Good morning, everyone. So thank you for joining our Eupraxia seminar series today. And thank you very much to Dr. Marie Labat from Synchrotron SOLEIL, who's going to deliver the session this morning. So the title of her talk is COXINEL towards compact free electron lasers. So just a few little pieces of housekeeping before we get started. We would love it if you've got questions to ask throughout the seminar or at the end. But I would ask that if you could just use the Q&A function, please, and put any questions that you've got in there, and then we'll put those questions to Marie later on this morning. And that's about it really in terms of housekeeping. So I hope you enjoyed the seminar, and over to Marie.
Thank you very much. So good morning to everyone. And indeed, it will be my pleasure today to talk about COXINEL, which is a project, let's say, maybe one path towards more compact free electron lasers. So before going into the deep of the subject, I will just make a few recalls about what are free electron lasers. So free electron lasers are in fact lasers, but with an original gain medium. And this gain medium consists of relativistic electron beam wiggling in a periodic magnetic field, plus a co-propagating electromagnetic field, so a radiation. So the relativistic electron beams are produced by what we call an accelerator. The periodic magnetic field is produced by what we call an undulator, which is an assembly of magnets with alternating fields, so that when the charged particles go into this periodic magnetic field, they will oscillate transversely. So they have a sinusoidal trajectory. And the core of the principle of free electron lasers is that we will have an interaction between these transversely wiggling electron beams with an electromagnetic radiation. And with this interaction, we will have energy exchange between the particles and the field. And the particles will be, thanks to this interaction, modulated in energy. And this modulation will occur at what we call the resonance wavelength, which is defined here, and which depends on the period of the magnetic field, the strength of the magnetic field, and the energy of the electron beam gamma. So with this interaction, we will have an energy modulation. And since we have dispersion along the undulator, this energy modulation will be converted into a density modulation, so that we will have creation of micro bunches within each bunch, and each micro bunch will be separated by this wavelengths, resonance wavelengths lambda r. And thanks to this micro bunching, we will have emission of an additional coherent radiation, again at this period, so that we will have a signal, a light produced proportional to n, the square of the number of electrons. And this additional radiation will be then self-amplified in an exponential regime until a saturation is reached. And what you see on this plot here is the evolution of the FEL power along the undulator. And you can see here an exponential growth until a saturation is reached. So at the exit of the undulator, we obtain a radiation at this resonant wavelength, which depends on the beam energy and the parameters of the undulator. So as you can see with this formula here, the big advantage of free electron lasers is that they do not have any intrinsic limit in terms of wavelengths. If you want to go to very large wavelengths, you just have to play with the beam energy by reducing it or increase the magnetic field. And the other way around, if you want to go to very short wavelengths, you only have to increase the beam energy gamma or reduce the periodic magnetic field, the period of the magnetic field. So we can go to very short wavelengths. And actually, FELs are the most powerful sources when we look at the hard X-ray range. Now, how do we do to characterize the performance of a free electron laser? Well, just as in the case of standard lasers, we refer to a gain. And how do we define the gain? In fact, more usually we use not the gain directly, but what we call the gain length. It's a very helpful parameter because it enables to have an idea of how long will be the undulator before reaching saturation. So typically, if you obtain a gain length of 1 meter, it means that within 2 or 3 meters, you will reach the saturation. And this gain length is defined as following. We have here, again, the period of the magnetic field, the beam energy, the beam size, and the peak current. So what is very important for you to remember is that if we want to have a short gain length, so that we rapidly reach the saturation in a free electron laser, we have to have a high quality electron beam, meaning very small beam size and very high peak current. And the higher is the beam energy, the higher has to be the quality of the electron beam to compensate the effect of this energy. So remember that the gain is essentially driven by the electron beam quality. Now, there are several FEL configurations depending on the type of radiation which is amplified and co-propagating with the electron beam inside the undulator. I just want you to remember the two main FEL configuration, which are the SASE and the seeded. So let's start with the SASE. The SASE is the most simple case. In this case, the radiation which is co-propagating with the electrons and which is amplified is simply the spontaneous emission of the electrons inside the undulator. This is the radiation that we call synchrotron radiation. So we just have interaction between the spontaneous emission and the electron beam, and the amplification is done along the undulator. The big advantage of this configuration is that it's very simple, and we can reach very easily the hard X-ray range by using very high energy beams. But this configuration delivers pulses which are not temporally coherent. So in fact, what we have at the end is a pulse which is made both in the time and the spectral domain with spikes, which can be annoying for certain applications. The second main configuration is referred as the seeded configuration. And in this case, we inject inside the undulator an external source, which is coherent and which we call a seed. And this external seed will trigger the energy modulation and then the density modulation step. And so we will have a transfer of the coherence of the seed to the radiation which is produced inside the undulator, so the FEL, so that in this configuration, we have a fully temporally coherent pulse at the exit. Of course, the problem of this configuration is that if you want to go to very short wavelengths, then you have to find a seed also at a very short wavelength to trigger the process, which is not that easy. So historically, free electron lasers, so they were invented in 1971, and they developed on what we call radio frequency accelerators, which are the conventional accelerators, taking advantage of the fast developments for the high energy physics. And you have now many FEL facilities around the world which deliver very high quality radiation from the terahertz to the hard X-ray range. And on this map here, you can see all the facilities already in operation and some projects. So let's speak now a bit about the last developments of free electron lasers. So let's say that during the last few decades, the developments mainly addressed the pulse quality and pulse tailoring. So we had many developments which enable to increase the temporal coherence of the pulses, even in the SASE configuration, which address also shortening of the pulse duration, multicolor operation, so having a laser at the end with multicolor, and also the possibility to vary the polarization of the output radiation. More recently, let's say that the main topics are the generation of high-intensity terahertz pulse, going towards high repetition rates. So typically on radio frequency linear accelerators, the repetition rate is about 1 kilohertz, and people would like to go to the megahertz range. There is also, of course, the issue of energy consumption saving, trying to make machines which are using less power, and compactness. So I will focus on this point while addressing FEL compactness. So if you remember the formula of the wavelengths of a free electron laser, which is recalled here, you can immediately see that if you want to go to very short wavelengths, like sub-nanometer radiation, you have to increase the beam energy. And typically, to get below the nanometer, you need giga-electron volts electron beam. The problem is that on radio frequency accelerators, the gradient that you can reach is limited to about 100 megavolts per meter. So if you make the calculation, this means that if you want to produce gigavolt electron beams, you need LINACs, so linear accelerator, which are typically several hundreds of meters long. You have here on this little sketch the footprint of the European XFEL, which is in operation now in Germany. And you can see that the length of the accelerator is 1.4 kilometers to provide 14 giga-electron volt electron beams. So what you have to remember is that to make short wavelength FELs, it corresponds to very large scale facilities. And the question is, how can we make more compact free electron lasers? So basically, we can consider that there are two strategies. The first one would be to try to reduce the beam energy and the undulator length, relying on what we call advanced compact schemes, such as, for instance, the eco-harmonic generation. And the other strategy could be to reduce drastically the accelerator length. And in this case, one way could be to use laser plasma accelerators. So, laser plasma accelerators. So the concept of plasma acceleration was proposed in 1979 by Tajima and Dawson. And the idea is to use ultra-short and relativistic intensity laser focused into a gas. And these high-intensity laser pulse focusing in a gas will generate a plasma housing micron-size accelerating structures. And inside these micron-size accelerating structures, we can reach accelerating gradients of 100 gigavolt per meter. So it's 3 orders of magnitudes higher than the one we can reach on the radio frequency accelerators. So it was a very nice concept. And thanks to the advent of laser chirp pulse amplification, this concept was finally demonstrated in 2004 by 3 groups in parallel, and they enabled to obtain quasi-monochromatic electron beams, which means with an energy spread which was below the 10%. So immediately after this demonstration, some guys had the idea to use plasma acceleration to operate a free electron laser. And they suggested that we could make what they call tabletop free electron laser. So tabletop is a little bit exaggerated, because if you consider that an undulator is at least a couple of meters long, and that to house these very high intensity lasers, you need a building which is typically a small house, it will never fit on a table or a very, very large table. But still, the idea was really to take advantage of this technology to reduce the length of the accelerating stage from 1 or more kilometers down to the centimeter. So, of course, a lot of groups tried to make an FEL using a laser plasma accelerator. So the race, let's say, started in 2008. And for more than a decade, we were several groups trying to operate an FEL on a plasma accelerator, but none of us succeeded. And we were only observing the spontaneous emission of the electrons inside the undulator, which is what we call the synchrotron radiation. Why did we all fail? Because simply at that time, the quality of the electron beam, which was produced in laser plasma accelerators, was not enough to fulfill the requirements for a free electron laser. And mainly, the main difference was regarding the divergence, which is over a few millirad, the emittance, and the energy spread. Those 3 parameters were really too high to obtain a gain for the free electron laser. So, starting from this statement, which strategy could we target then, just to try still to make a free electron laser on a plasma accelerator? So let's say that there were 3 possible strategies. The first one consisted in just waiting for the LPA performance to improve. The second one could be to couple a radio frequency injector with a plasma accelerator. And the third one was to find some tricks to use the beam as they were. So regarding the first strategy, it could be a good strategy because the LPA developed very rapidly, and since 2004, so the first generation, many techniques were implemented to improve the beam quality, the beam reliability, etc., with several techniques that I've listed here, and you can just go after to have more details. The second strategy, so the idea is to produce an electron beam in a radio frequency accelerator, so a beam with a very good quality, and just use plasma accelerator to post-accelerate this beam to high energies. But so starting from already a high quality beam. And the last strategy was to find some tricks. So there were basically 3 tricks proposed. I will focus only on the last one because the first 2 were never tested experimentally. And also because the last one was the one which we are using now on COXINEL. So the trick is in fact a trick in 2 steps, which are decompression and then chromatic matching. So let's start with decompression. So as I said before, the problem of the beam exiting from a plasma accelerator is that they have a very large energy spread, okay? And this large energy spread is killing the gain of the FEL. But if you use this beam and put it through a chicane, the chicane will stretch the beam and sort the particles in energy. So you have in blue here the low energy particles, and in red ahead the high energy particles. And what you can also see is that now, if you look at one small piece of the beam here, so one slice, locally the energy spread is very much reduced. So with this trick, you can locally reduce the energy spread so that you can enable locally the FEL. You increase the gain locally. The second step is, so you restart from this stretch beam, and the idea now is to focus this particle distribution along the undulator according to the particle energy. So you use a set of quadruples, and you tune those quadruples so that at the entrance of the undulator, you start by focusing the low energy particles. Then in the middle of the undulator, the middle energy particles, and only at the end, you focus the high energy particles. And the trick is that if you manage to tune the quadruples so that the advance of this electronic waste is synchronized with the advance of the light along the electron bunch inside the undulator, will synchronize the two slippage. You have to remember that the light is traveling faster than the electrons inside the undulator. So if you are starting to make a little FEL signal at the rear here of the bunch, it will progressively shift along the bunch when we travel along the undulator. But if you synchronize this waste with the advance of the light pulse will always see inside the undulator the waste, so the maximum electronic density. And if you remember, maximum electronic density means maximum gain. So it's a good trick to maximize the gain all along the undulator, and which will significantly speed up the FEL amplification. So this trick is the core of the COXINEL project. So COXINEL was started in 2013, and COXINEL stands for Coherent X-ray Source Inferred from Electrons Accelerated by Laser. And we received the financial support from Europe, an ERC grant in 2013. And the concept of the whole project was to use the existing laser plasma accelerator of the LOA, so Laboratoire d'Optique Appliquée, which is in France, use this double trick of decompression and chromatic matching so that in one single undulator, in a seeded configuration, we wanted to demonstrate the first free electron laser based on a plasma accelerator at 270 nanometer, so in visible close to UV range first, and then move on to short wavelengths at 40 nanometer. This is the experimental setup of COXINEL. So we go basically from left to right. So you have first, of course, the laser plasma accelerator. So you have here the electron beam parameters that were produced initially at the LOA. So a beam energy of 175 mega electron volts, a large energy spread, 20%, large divergence, 4 to 5 millirad RMS, and a charge density below 1 picocoulomb per MeV. This beam, when it exits the gas jets, which we can see here, is first captured by a triplet of quadruples, which are made of permanent magnet, and they are variable so that we can change the gradient of the quadruples. And this set of quadruples enables to immediately refocus the beam, because since we have a very large divergence, we really need to refocus immediately, otherwise the beam will explode. After this triplet, we found our magnetic chicane, so the chicane which we do the decompression of the electron beam, but also the energy sorting of the particle, and so the reduction of the slice energy spread. After the chicane, we can find 4 standard electromagnetic quadruples, and these are the quadruples which we will use to make the chromatic matching. So this spatial focusing, taking into account the energy of the particles inside the beam. Of course, after this, we have an undulator. It's an in-vacuum undulator with a period of 20 millimeter and a Ku of about 2.5. And this undulator produces spontaneous emission, of course, but it's also where the gain is developed, so where the electrons are wiggling to interact with the radiation. Talking about radiation, so as I said, COXINEL is operated in a seeded configuration. So we use a seed. And this seed is generated by taking a little branch of the main laser, which is doing the electrons. So we just capture here a small branch of the laser, and we focus it into BBO crystals to make frequency tripling of this infrared main laser so that we can obtain a radiation at 268 nanometer. And we do a little bit of temporal and spatial filtering before injecting this seed with a flat mirror here, which is located inside the chicane. At the end of the beamline, we have a dipole, which is dumping the electron beam on the side so that we can leave the radiation going straight towards the diagnostics. So in terms of diagnostics, I will first describe a little bit the electron beam diagnostics. So to know where is the beam, to optimize the focusing of the beam, to check the orbit and so on, we use screens. So they are based on YAG or LANX screens. So when the beam hits the screen, it produces fluorescence, and you can image this distribution on the camera. And you have here example of the beam distributions all along the beam line. And to measure the charge of the beam, which is a very important parameter, we use turbo ICTs, so integrated current transformers. And we have two of them, one at the beginning of the beamline here and one at the end of the beamline here. And these two devices produce absolute charge measurement. Regarding the timing diagnostics, so we use what we call a streak camera. It's an Hamamatsu streak camera, and the idea is to use this device to adjust the delay between the seed and the electron beam inside the undulator. So of course, if we want to have an interaction between the seed and the electrons, we have to make sure that the two are arriving at the same time inside the undulator. And so this camera is recording the seed pulse and the spontaneous emission of the electrons inside the undulator. And so we overlap the two on the screen, as you can see here, and we adjust the delay line of the seed so that we can finally overlap the electrons with the seed. And finally, our main photon diagnostics, it's a 2D imaging spectrometer, which enables to image the light at the exit of the undulator. So it's a device which provides the spatiospectral intensity distribution. So you have here an example of what is recorded by the spectrometer. So along the horizontal axis, you have the wavelengths, and along the vertical axis, you just have the vertical distribution. So on the first image here is an example of the seed alone. So you have a nice Gaussian distribution in both planes. And on the second image here, you have an example of the spontaneous emission of the electrons, so the synchrotron radiation, which is quite noisy and very broadband. And on this last image here, you have the case where we overlap the seed and the synchrotron radiation, which is the case where we should see our free electron laser. So the first experiments at LOA in France enabled to demonstrate the first LPA beam control transport. So before, people were just throwing the electron beam inside the undulator to see if it could produce an FEL. We were the first to try to really transport properly with nice orbit and a nice optics of the electron beam all along the beamline. So it was a very important first result. And with this nicely transported beam, we could also observe the first narrowband synchrotron radiation. So we managed to tune the gap and play with the energy spread of the beam to obtain a narrowband synchrotron radiation emission. But we could not observe any FEL, and the reason was that the divergence, in spite of our tricks, was still too high, and the charge density was too low. And this is why in 2020, we decided to move COXINEL to Germany, and more specifically to the Helmholtz-Zentrum Dresden-Rosendorf Center, so located in Dresden. So why did we choose to go there? It's because their beam properties appear to be much more suitable for an FEL demonstration. Indeed, they had a charge which was nearly 1 order of magnitude higher than the one at the LOA, a smaller divergence, a smaller emittance, and very important, a much better stability. They were at that time already able to operate during more than 8 hours in a row of stable operation. So we moved in 2021, and you can see here the 3D representation of the COXINEL beamline, which is in color here, and which was plugged just at the exit of the laser plasma accelerator facility, which is in gray here. And you can see here the picture of the room. So here you can distinguish the gray boxes, which is housing the laser plasma accelerator. And in row, you have here in red the chicane, the quadruples in blue, and you can see this pale green here, which is the undulator. We took about 12 days to commission the whole beamline, so testing all the diagnostics, the transport of the electron beam, and the characterization of the electron beam at the source until the end, also all the photon diagnostics. And we were ready to start FEL experiments in January 2022. But meanwhile, so let's say end of 2021, the first plasma-based FEL signals were reported. And so there were mainly two reports. The first one were the Chinese from the COMCAS team. So in their case, they used an electron beam at 500 mega electron volt with an exceptionally low energy spread, 0.5%. If you remember, when we were in France, we had 20%. So 0.5% is really low. A divergence of 0.2 millirad, and still with a high charge. And so they managed to operate their FEL in a SASE configuration and to obtain lasing at 27 nanometer. So this team, let's say, chose the strategy number one, so to improve the LPA beam. Just a little remark, we do not know anything about the stability of their FEL and the reliability. They published this result, but we don't know anymore. The second team which reported the observation of a free electron laser is the Italian one from Spark. So in their case, it's more the strategy number two. So they used a beam produced in a radio frequency accelerator, and they added a small stage of plasma acceleration, few mega electron volts. And they managed to operate their FEL in both configurations, in SASE and in seeded, to produce FEL at 800 nanometer. I would say that this result is slightly different from the one of the Chinese and from the one that I will now describe on COXINEL, because it's just a small stage added to a radio frequency accelerator. It's not full laser plasma acceleration like in China or on COXINEL. There were also some encouraging results from Berkeley. They were starting to see a coherent radiation at 400 nanometer. So now on COXINEL, so in spite of these results, and we knew that we were not the first one anymore, we still carried on our plan because we were the only one targeting an operation in a seeded configuration. And so we started the experiment as planned in February. And during the first delay scan, we could observe this very, very small signal that you can see here, but which was the first trace of an FEL. After some optimization, let's say that this is the summary of our first results. So you have here, all these images are spatial spectral distributions of the radiation. Along the first line is the experiment. And we have here in the first column, the synchrotron radiation only, so no seed injected. Here is the seed only, so when we don't have any electrons. And if we put the two together, so electron beam plus seed, we obtain this shape here. And you can see on the right side here, something like a little nose, which is the additional FEL contribution that we generated. If we subtract to this image the seed, we obtain what we call the isolated FEL trace, and you can now clearly see the additional coherent emission that we produced. The bottom line here is simply the simulation of our case, and as you can see, we could obtain a very good agreement between simulation and experiment. Now, what you can also see on this set of images is that our FEL signal is quite peculiar. Indeed, I said at the beginning during the introduction that when we seed, we inject a seed at the resonant wavelengths and we trigger the modulation, the energy modulation and the density modulation to obtain a free electron laser, but at the same wavelength as the seed one. Whereas here, what we see is that the signal we are producing is redshifted with respect to the seed, and significantly redshifted. And the second peculiar thing is that in between the seed and the FEL, we can see some fringes. So why do we have those two peculiar signs? Let's start with the redshift. So if you remember well, after the chicane, we have a strong chirp on the electron beam, which is what we can see here. So we have a strong dependency, a strong correlation between longitudinal position and energy. Now, if we zoom inside this distribution, zoom very strong, so down to the scale of 1 seed wavelength or 1 resonance wavelength, we can see the following. So this is the seed period, and this is the particles along longitudinal axis. And you can see that at the scale of this period, the particles at the rear here have much lower energy than the particles here ahead, which means that when the energy modulation will occur, so you see here, particles are modulated in energy, and we drift inside the undulator. This modulation period, because those particles here will travel much faster than the ones here, we will have a stretching of the modulation period along the undulator. And if you stretch this modulation period, you also stretch the emission period, which means a redshift in wavelengths. So I will not go into details, but just believe me, this stretching of the modulation wavelengths can be very easily computed, taking into account the speed of the particles along the undulator and so on. And you can obtain here a formula to predict the wavelengths of the FEL as a function of the wavelengths of the seed, of the beam energy, the parameter of the chicane, because of course, if you change the chirp, you will change the stretching. So in summary, what you have to remember is that we have a redshifted FEL because of the strong beam chirp, which causes a stretching of the modulation wavelengths, and that this stretching can be easily computed analytically. So we can predict at which wavelengths we will have our FEL. Now, regarding the fringes, in fact, these fringes are interference fringes produced because we have two coherent pulses separated in wavelengths. And if you have two coherent pulses separated in wavelengths, they interfere and they produce fringes in both time and spectral domain. But if you put this observation the other way around, you can also say that if we observe phase-locked fringes or interferences, it means that we have two coherent pulses. Of course, the seed, we know it's coherent, it's a laser, but also the FEL. So by observing those fringes and their phase lock, we demonstrated that our FEL was temporally coherent. And this was a real additional progress with respect to the work of the Chinese, which operated in the SASE configuration. So SASE means no temporal coherence. Okay, so with these first results, we were very happy, but we were still in very low gain, and we know that we had a lot of margin of progress, so we kept going on with new campaigns of experiment. And so in 1 year later, in 2023, we made a campaign to work on the FEL tunability and the modeling of this tunability. So on standard free electron lasers, you have here the formula of the FEL. So if you want to change the wavelengths of your free electron laser, you can play on the beam energy or on the period of the undulator. But once the undulator is installed, you cannot play anymore with the period. So it's not a real tuning parameter. You can play, however, with the strength of the undulator by playing with the distance between the magnets. So you have these two nodes to tune the FEL wavelength. But this works only if you are in SASE, because if you are in seeded, you still have to match the seed wavelengths with these resonance wavelengths. So if you want to change your FEL, you also have to change your seed. And this is also not that easy, because once you have a coherent laser to inject, changing the wavelengths is not that easy. You can go to the harmonics, for instance, or use OPA to tune a little bit, but it's not that easy. In our case, thanks to this redshift mechanism, we showed, so as I showed you before, we have this formula here, which means that without touching the seed, without touching the electron beam parameter, without touching the undulator, you can play only with the strength of the chicane, so the strength of the field inside the dipoles, to change the FEL wavelength. So it's one first knob for the FEL tunability. Then in 2022, we refined a little bit our model, and we introduced the chirp of the seed so that we have a longitudinal dependence of the seed wavelengths. And this gives two additional knobs with the delay of the seed with the electron beam, tau, and the chirp of the seed. You can change the chirp of the seed, for instance, by inserting few silica rods or something dispersive on the seed path. And then in 2023, we made one more step in the refinement of this model. So this time I will skip the math because it's the formula would take just my whole slide. So I will just ask you to believe me. If you introduce the temporal dependence of the resonant wavelengths, because the energy here depends on time, you can see that you can have, in fact, you can picture the wavelengths of the seed in blue, which depends on the position along time, because the seed is chirped. And it's the same for the electron beam. In fact, the resonance wavelength varies along the electron beam because the energy varies along the electron beam. So by changing any of the parameters, for instance, the K of the undulator or the delay between the seed and the electron beam, you can move the resonance all along the beam. And by moving the resonance all along the beam, in fact, you can tune the FEL wavelengths in a large space. And we have now 4 knobs to tune the FEL: the chicane strength, the delay between the 2 pulses, the chirp of the seed, and the strength of the undulator. All this without having to change severely the seed or to remove the undulator. And so this campaign was made to demonstrate this new model. And we could confirm that the model was correct as a function of the strength of the undulator, so Ku, and as a function of the delay between the 2 pulses. Now, a second point of this second experimental campaign is the following. So we suggested that the transverse face of our redshifted FEL had a V-shaped, so V like the letter V. And this was due to an inherited from synchrotron radiation. So if you look at this picture here, you have the mechanism of the redshift, which now you know. So you have a stretching of the FEL wavelengths with respect to the initial resonant wavelengths. And if we now look at the spectrum, we have here the seed wavelengths and the additional FEL. And now if we look at the face, the transverse phase, if we look at the transverse phase here at the resonant wavelengths, it's parabolic as expected. But now if we look at the transverse phase on the red side of the resonance, so where is the FEL, we obtain this V shape. Okay? And this was not known. We know that the FEL properties are inherited from synchrotron radiation, but it was never pointed out that the face of the synchrotron radiation on the red side of the resonance was V-shaped. And so we tried to demonstrate this experimentally. And how could we make this? Just by observing first the shape of the fringes. Indeed, the shape of the transverse face will influence the shape of the fringes we obtain here when we make interference between the seed and the FEL. And you can clearly see on this here, this is the simulation, but you can see that the fringes are not smoothly curved. They are more with an angle like a V. And this is only due to the V shape of the face. So this is the simulation in the perfect case. This is the simulation in the case where the seed is not aligned vertically with the FEL, which is our experimental case. And this is the measurement. And we can clearly see here on the measurement that we really have this peculiar V shape of the fringes. And the beauty of this V face shape is that if you backpropagate such a shape, it will lead to phase aliasing. And phase aliasing corresponds to zeros in intensity. And 0 in intensity means fringes. So let's say additional fringes. And if you track the contrast of these fringes while backpropagating the radiation, you will have a maximum contrast at the source point. So this is what you can see on this example here. Let's say that we focus on this image here. Here is along the line here is the radiation at the exit of the undulator. And when we backpropagate, you can see here that we have some little fringes appearing on the top and the bottom of the high intensity spots. And so if you measure the contrast to track, you will see that you will have a maximum around this point here, which will correspond to the source point. So this means that if we manage to backpropagate the radiation, track the new fringes, and observe where is their maximum contrast, we have a way to retrieve the source point location. And we did it. So how did we backpropagate? Simply by using our imaging system. In fact, to collect the radiation on the spectrometer, we use a pair of lenses. And these lenses are mounted on a remote, translation stage, so that we can choose where we are imaging the radiation inside the undulator. And so by sliding a lens, we can just choose, okay, I'm imaging the exit, or a little bit, let's say 5 centimeters before the exit, 10 centimeters, etc., until going back to the entrance of the undulator. So we slided the lens so that we could record the radiation, as you can see on this picture here. This is the radiation nearly at the exit of the undulator, so minus 10 centimeters, and then more upstream, minus 0.4 meter, etc., etc. And we can clearly see that only here, you have the zoom here, we can see the additional fringes. It's where at minus 0.5, minus 0.4 is where we found the maximum contrast of this new fringe. And below is the corresponding simulation. And you can see here more clearly the additional fringes. So the vertical ones are the interference between seed and FEL. And those new ones here are just the effect of this V-shape aliasing when you backpropagate. So maybe I don't see your face since it's a webinar, so maybe I've lost many of you with this V-face shape and V-face effects that we took advantage of. It doesn't really matter. The only thing I want you to remember is that with the beam we had in Germany, we managed to do some very refined FEL physics. So we managed to really push the understanding of FELs on a plasma accelerator. And it was a really important step for the community. I will now move on to the last experimental campaign. So the last one was last year in 2024. And this time we really had an excellent beam. So we had more charge than before, 10 picocoulomb per MeV, energy spread of 7%, and a beam which was exceptionally reliable and reproducible. So we had nearly 2 weeks of experiments. And during these 2 weeks, we could operate during 8 days for 10 hours a day. And we basically had always the same beam parameters. And this is very important because it means that you can now think about doing experiment where you are testing one setting on the first day, and the second day you trust that your beam is the same and you can vary another parameter and you can compare from one day to the other. And this is really the first time that we could do this. Before, we had to rush to record series that do not we are only comparing data at the scale of half a day, not more. And this time the beam was so reliable that we could compare from one day to the other along 8 days. And thanks to this, we could finally vary the last parameter that we had not tested for our model of tunability, which was the chirp. Because to change the chirp, we have to remove some pieces of fused silica and realign the seed and so on. So it's not very long, but it's not 1 second. So it was better to do one chirp one day. And so that's what we did. And we can see on this picture here, the first row are the experimental images. So you have here the case of a seed with a very large chirp. And you have here the second case where we removed all the fused silica and we had the minimum chirp. And all the images are normalized to the seed intensity. And you can see that in the first case, the FEL is barely at the same level of the seed, but that with the minimum chirp now, the seed is at least 4 times higher in intensity than the seed. So a much better amplification of the FEL. The bottom line here, again, is the corresponding simulation. And you can see that we had very good agreement between simulation and experiment. Thanks to this very short seed pulse duration, we wanted to know where we were in terms of the gain curve. So this curve, which is supposed to go exponentially and then reach saturation. And you have here in red the case of the shortest, the smallest chirp, and in green the longest chirp. And you can see now that according to the slope of this plot here, and especially here, the way that we don't have any more this curved behavior here, which is the coherent regime. We directly go into the exponential regime. And this is where we are now. So this means that we could observe last year that we are now in the exponential growth regime, and the quality of the electron beam enables to have a high gain FEL. And so, as I said before, the idea was to check the last knob of our model, so the chirp, and you have the results here. So when we vary the delay, which was the first knob to vary the wavelengths, if we take, for instance, the longest seed duration, so the maximum chirp, we have this green plot here. This is what we had published already in 2022. And now we change the chirp and we redo another plot. And so it's the blue one with a different chirp. And with the smallest chirp, we have the red one. So the dots are the data and the line is the model. So you can see that with these measurements, we could confirm that our model also works as a function of the chirp. So what are the next steps for COXINEL? So we have now with us a new PhD student, and she's working on the reconstruction of the FEL temporal profile. We would like to take advantage of those many fringes that we have to try to infer the FEL duration. And of course, we would also like to reduce the COXINEL wavelengths and to go towards shorter wavelengths. And the idea is first to implement a new spectrometer, which can go into vacuum, to try the observation of the FEL harmonics. So I didn't talk about this, but on a free electron laser, you have the fundamental wavelengths, but also all the harmonics which are produced which are automatically produced with the same mechanism. Of course, they have lower intensity, but they are produced. And so we would like to, as a start, observe the harmonics of our FEL, so at 90 and 54 nanometer, to make a first step towards shorter wavelengths. I will now reach my conclusion. So let's say that laser plasma-based free electron lasers are still in the early development phase. But just remember that the first free electron lasers were proposed in 1971, and it took nearly 40 years for the first FEL to laze in the X-ray range. So 40 years of development. While in the case of plasma-based FELs, they were proposed in 27, and we are now we obtained the first lasing in 2021. So it's, let's say, 15 years of development. So we can consider that we still have like 25 years to improve, and let's give us the time to keep this improvement. A remark about the stability: maybe laser plasma accelerator will never reach the stability of the radio frequency accelerator ones for intrinsic physics and reasons. But I'm still convinced that there might be some applications where we are more interested by the compactness of the facility than the stability. So we can make a compromise. Maybe it's not as stable, but it can fit in a much smaller space. And well, within all this framework, I'm happy to work on COXINEL because I think COXINEL is helping at least to try to see if we can make a compact FEL compatible to users, because for now we have demonstration that we can operate an FEL, we can laze, in the UV, in the X-ray range, but for the moment, no one has demonstrated that the stability is good enough for some users' experiments to be produced with these beams. And that's why we want to reduce the wavelengths on COXINEL, is to target, like, let's say, a radiation at 40 nanometer to test our beam with users behind and see if it matches. And I think I'm done. So if you have questions, just please go ahead, and thank you very much for your attention.
Thank you very much for your talk, Marie. We do have a couple of questions. If anyone has any further questions, please put them in the Q&A and we can put those to Marie just now. So the first question is, how can we suppress energy dispersion through the FODO lattice before the entrance of the undulator section?
We cannot suppress. The lattice cannot suppress energy spread. Energy spread is here. The lattice can rearrange the particles in the phase space, like putting some energies on one side and so on. So with this we can play, but the energy spread will always be there. One possibility would be to cheat, and what you could do is to disperse the beam in the chicane and cut with a slit low and high energies and then recombine. It can be a way to clean the energy spread. But it's not the lattice which is doing this. It's an external piece of slit. I don't know if I answered correctly the question. Your microphone is off.
Sorry, thank you. If the person who asked the question has any follow-up, then feel free to put it in the Q&A. Another question that we've got is on the slide about the beam line. You presented the electron beam parameters from LOA, but your experiment was done on the Draco laser. So were the electron parameters the same in Germany?
No, that's why we managed to obtain FEL in Germany. So the parameters are these are the, so when we left, okay, so these are the parameters we had at LOA. So just focus on the 20% energy spread, 4 millirad divergence, and 1 picocoulomb charge density. And when we arrived in Germany, the starting point was this was the ideal starting point. But honestly, when we started, we were at 5, 1, 1. And now at the last experiment, the charge density is now twice, because we are, oops, we are now at 10 picocoulomb. So a little bit at the cost of the energy spread and the divergence, but by optimizing the transport for the divergence, we took quite a big benefit from this peak, from this charge. So yes, the parameters from Germany are really different from the one at LOA. And this is why we succeeded to have this FEL signal in Germany, but not at LOA.
Thank you. And we've got some more questions coming in. So the next one is, can you use quadrupole magnets paired with collimators to clean the beam and reduce the energy spread?
Like collimators is what I said before, it's slit. Yeah.
Okay.
Yeah, it's the same idea.
Okie dokie. And the last question we've got is, what simulation codes did you use for the simulations presented in the slide explaining the V shape of the fringes?
That's a good question. So we used many codes. So to be sure that this V shape here of the shape of the face was V on the red side of the resonant wavelength in the case of synchrotron radiation, we purely took the book of Hoffman, so one of the guys who wrote in detail the theory of synchrotron radiation, and we coded his equations in a Python script, but quite a heavy integration of the equations. And we confirmed that we had this V shape here. And if you look here, we compare the black one or the blue one, I don't remember. I think it's the blue one. The blue one is really the Hoffman calculation of the synchrotron radiation phase. Okay, so that was the starting point of the simulation. Then to do the FEL simulations, we use Genesis. So the advantage of Genesis is that it computes everything, but it's a black box. So we reproduce the V shape, but we don't know where it comes from. So that's why we preferred to start with the analytical model so that we were sure of what we were doing. And we compared. So, and you can see that the phase of the FEL simulated with Genesis perfectly overlaps the one predicted by synchrotron radiation theory by Hoffman. So basically we use two codes, and one analytical to really understand the physics, where it came from, and the second one, Genesis, to check that it applies correctly to FEL and to reproduce our experiment. Sorry, my answer was a bit long, but...
No, it's perfect. Thank you. And we have another question that's just come in. Will you continue experiments after the upgrade of the Draco laser, and will you expect higher electron energy and shorter radiation wavelength from the undulator?
Well, there are several questions in this question.
Yeah.
So there is a Draco upgrade, which is expected. I think it's within a year or a couple of years. And yes, we expect, we don't expect higher beam energy. We could make higher beam energies already now. We are working at 190 MeV. We could make higher beam energies. The problem is that if we increase the energy, as I said in the introduction, you reduce the gain. So if you want to maintain the gain at a higher beam energy, you have to increase the charge. And presently, we can't. The guys of the laser plasma accelerator, they can increase the energy, but with the same charge. So we know that we will not have enough gain. With the upgrade of Draco, we hope to have more charge so that we could increase the energy. That's the first point. The second one, to reduce the wavelengths, we can increase simply the electron beam energy. So the undulator will, if we want to reduce, we just have to increase the energy. The problem is, as I said before, that we also have to change the seed. If we want to let's say operate at 40 nanometer, then it means that we need also a seed at 40 nanometer. And so one of the strategy is to use harmonics in gas as a seed, which was done already in FLASH or in SCSS in several experiments. So we know that it's doable. The other strategy is to go towards more complex configuration where you seed in a first undulator with our seed at 270. And then when you go to a second undulator, you amplify the harmonics which were produced in the first undulator. It's a way of cascading and going down in wavelengths. But for this case, we need two undulators, which is in our plan. By 2027, we hope to be able to operate with two undulators.
Okay, that's brilliant. Thank you so much for your time this morning. It's been a really great seminar. And thank you for all of our attendees for coming as well. Just to let everyone know, the next seminar in the series will be taking place on Friday, the 5th of December at the same time, 11 o'clock UK time. And it will be Professor Massimo Ferrario. And he's going to be talking about driving into the plasma waves, beam-driven wake-field acceleration at Eupraxia at Spark Lab. So if you're interested in that, please make sure that you come along then. But once again, thank you to Dr. Marie Labat. And yes, I hope everyone has a nice day.